get started. The first one speaker, welcome. Please louder.
Today I will present our research named by ACCD Answer Review Solutions, STHD, Lucia application. This is the outline of my presentation. First, in the introduction, I will briefly introduce the physiological fundamentals of ECG signal of the primary type of noisy cavity in the body, which is the calendar. Next, motivation section will highlight the three critical challenges we undo the test. To tackle this problem in the methodology section, I will explain our proposed application and algorithm improvements is included. Finally, I will present our current experimental results and wrap up the conclusion. As we know, ECG is a crucial non-invasive tool for diagnosing cardiovascular disease. As shown in the video below, the complete cardiac cycle consists of the T-wave, QRS complex, and C-wave, preserving the exact morphology of these waves is critical. For instance, the steadiness of the QRS complex is linked to ventricular depolarization, while the stable function of the ST segment is key indicator for diagnosing myocardial infarction. However, in real-world clinical settings, low ECG signals are highly susceptible to diagnosis. Among them, the most troublesome is baseline window. Baseline window is primarily classified patient with resolution and electro-independent change. The critical challenge with baseline window is the low frequency noise, typical below 0.5 Hz. This means its spatial distribution heavily overlaps with the low frequency components of the ECG itself. When served baseline window occurs, it causes irregular location along the baseline, which directly distorts the ST segment and can lead to the clinical misdiagnosis. To tackle this, various deep learning models have been proposed. Essentially, the ECG application, which is based on a space-based model, has achieved remarkable success. It provides a true long-range sequence model with linear frequency distribution. Therefore, we expect the ECG as a baseline application for further investment. Next, we will examine the three key arguments currently facing the noisy model that is highly asked to address. First is the internal cell of the full-time voltage flow. STFC is largely used to harmonize ECG signal to a 2D phase diagram. We use a short window, we capture the short QRS complex but fail to isolate the low frequency baseline window. Conversely, a long window captures the noise trend accurately but smears the temporal details. A single window size simply cannot have the base for work. Second is the challenge of the post-patient generalization, because patient cardiac efficiency is always closely with the mean. Model training on a database transfer on domain shift and continuation. Furthermore, collecting massive amount of data for every new patient is clinically impressive, highlighting the traditional models cover around the shelf pitch of the ECG waveform. Because conversion loss function like USB focus on the point-wise absolute errors to minimize the frequency risk. The network change output a steady mix, occasionally raising high frequency transmit features like the state loss of the QRS complex. The type of meteorological distortion can directly lead to misdiagnosis in cardiology. To resolve the SDM feature, we propose a group solution architecture built upon the MECG waveform. Showing the architecture diagram, we utilize show window SDAP as the main path into the resolve the share. High frequency transmit feature in parallel, we introduce a long window SDAP to capture the low frequency baseline window. The key innovation here is that we do not simply alternate these two features, we could cut the time zero. Instead, we use the Android KT module to treat a long window feature as a condition generator of the testing to a 1+3 stepwise convolution for frequency domain mapping. We generate a three modulation parameter gamma and theta. This parameter apply a non-basic scale shifting model modulation to the show window features. This frequency guides in the subsequent feedback by member network to test it with micro noise while completely within the risk of the central domain. As I mentioned, the long window feature acts as a condition generator. Therefore, test for stepwise convolution along the frequency axis. This is the kernel that is the tree 1+3. If the length is the smooth frequency spectrum without introducing an additional signal problem. These features are developing into the scaling factor gamma and the shifting factor beta. However, applying gamma and beta cause the entire background to destroy the QRS complex. To prevent this, we introduce the 2D gating mix. We compare the show window and the long window and use the 3+3 convolution to predict a probability mass ranging from 0 to 1. Showing the equation, the next monitoring with gamma and theta. But when the network detects a high frequency transient features like a QRS peak, the next value approaches the 0, effectively blocking the modulation. Conversely, in videos with low frequency baseline window, the net opens up to the low pressure relation. Finally, the dynamically success parameter are applied to the show window features for MIS image transformation, showing the parameters. To address the oversmoothing problem mentioned in model modification, we introduce the first order morphology resolving loss. Traditional loss function focus on between the absolute voltage at each point. Instead of doing that, or first order morphology resolving loss focus on the law of the signal. Showing the equation, we compute the first order kinetic difference of both denoising signal and the clear target by calculating the normal their difference. We force the model to match the speed slope of the QRS complex. To tackle the challenge of the classification generalization, we adopt the reptile meta-learning framework. First, in the test definition, we define 19 independent test cases of varying percentage baseline window noise, ranging from level 1.2 to 2.0 as for the algorithm. During the training phase, the inner loop attached to the state noise while using the SNW optimizer. After obtaining the test outer loop computes the parameter variation and update the global wise. The future detail based on metastasis explosion. We apply a linear decay schedule to explosion, which allows the model to explore orderly in the early stage and compress stably in the later stage. Through this iterative process, the framework successfully affects the global initialization file. As size closer to the micro solution across all node space. It lays a solid foundation for rapid social application in the future technical. Moving on to all experimental data, following the standard protocol from general studies, OETG fields are assembled to 360 Hz and segmented into 512 points window. Using for training and prediction datasets like screenshotting, baseline regular nodes of varying indices into the PhD report tool from clear nodes text. For comparison value of the denoising performance, we utilize 4 standard metrics. The first 3 SSD, MAD, and PRD mechanism is based on signal distortion and error. The lower value indicates better performance. Conversely, combined similarity assess methodological ability, where a higher value is admirable. This is my result. Table 1 on the left are completely unseen patient reports. That is on the level class setting where initializer Y is provided by all meta-learning framework converts extensively on outperform. Traditional training method across all metrics. Next, the table 2 on the right is perfectly valid or critical design. You can see that the dual solution architecture successful rationale of the SSD and reflecting the global error. Moreover, after incorporating the first order methodology training loss, maximum local distortion and maybe of the infection. This trick proves the waveform over smoothing problem has been successfully addressed. This slide provides a visual demonstration of how our first order methodology conserving loss trick improves the waveform reconstruction. Here we present the denoising results independent patient reports. Cell 15A14. On the left is the baseline model. As you can see, traditional point wise losses struggle with the peak frequency, resulting in clumping and over-smooth peaks. On the right side, especially the errors highlighted by the green circles are before correcting or proposed loss function. The model is compared to maintain loss persistence. Here you can see the laboratory report turning points and high frequency peaks of the QR context. It visually converts the more focal loss correctly and may eliminate the methodological distortion caused by oversmoothing. Finally, we present the future adaptation test. Operating on a per patient report basis, we extract a minimum number of K heartbeat segments to form the support set for single step function. The remaining mutually exclusive segments from the same patient are usually the priority set for evaluation. As shown in the table 3, even under the extreme condition where K plus 1, the model's PRD and cosine similarity achieve an immediate and significant improvement. SK increased to 10. All integration actually safely enough. It strongly proves the initialization, while a query for a core mechanic framework practice a highly robust post-patient realization technique. To conclude, by integrating a new resolution SDFT, the first order methodology serving loss and reptile mechanism is probably not only explore the time frequency resolution barrier, but also perfectly preserve meaningful concepts. Feature while achieving highly variable future rapid deployment. However, we do acknowledge current limitation in our clinical application. Right now, the adaptation still realize the high goal of a minimum number of PM noise pairs with a single signal pair. Therefore, for future worldwide, we explore the unsupervised or weakly supervised fine-tune efficiencies by overcoming this constraint. We want to further enhance the model's particle development and reduce the performance in real-world healthcare settings. This concludes my presentation. Thank you.
Any questions? Any questions? Okay.
Okay, thanks for your opening speaking. And I have one question for you. During the feature fusion of the Dual Window STFT, you implemented a 2D gate mask. I was wondering why didn't you singly add or concatenate the features from the long and short windows?
First, if we directly use add or concat, the full time resolution of the window activity or directly constraining the feature of the show window. Therefore, I use visualize linear modulation, treating the long window as a condition generator. The modulate the show window. This allows us to focus on capturing the low frequency noise without destroying the original time resolution. Next is the 2D gating mask part. In my model, after the show window features test for the recorder, the liquidity condition is reduced to 60. Since the activity output in cycles is arranged from low to high frequencies. My initial approach was to set a PC modulation range, only allowing the long window to modulate the low frequency region where the gain less than or equal to 3. However, the problem with this is that I cannot be certain that the effective range of the low frequency noise won't safely is daily. Therefore, I changed to use the 2D gating mask, allowing the model to get a probability mask from 0 to 1. Its own basis on the current time frequency features. Then, encountering high frequencies and noise of the waveform, and make the approach level to have the long window modulation. Consider in areas with low frequency preference. Next will open up and interpret. It ensures the high frequency features are minimally affected by the modulation.
Okay. Okay.
Why did you choose reptile as your meta-learning algorithm instead of the more commonly used NML? Also, could you explain how your reptile algorithm actually converges during training?
drive forward and it doesn't require user to spell the support set and the current set during training. Instead, it simply performs multi-step updates in the inner loop across the various defined tests. Then, the outer loop uses the difference in this parameter predictor to update the global wise and finding a global initialization y that is process the optimization solution or test. This approach is especially perfectly fit for beginners in text. So in my example, I define the 90 different extent of baseline render as the static text for this inner and outer loop updates. Which then I incorporate a linear decay strategy. This allows the model to furtherly explore the different tests in the early stage of the training, and then steadily converge in the later stages, right at the point closer to the optimization solution across all those nodes of tests.
I have a question. In your work, you come across meta-learning algorithm and dual resolution method jointly, right? Jointly. And return to your comparison page. But why do you compare your results separately? Because the left side is the meta-learning and the right side is the dual resolution. In my opinion, you seem to jointly combine it. 对，就是说为什么你们要分开？因为很多中美，
它原本
大概是用大三点。
它原本是这样子的，它如果左边的话，它原本是用平的，所以我左边画线，所以如说我今天换成用它的话，它可以得到比较好的指导曲状。对，它右边的话，它的那个single resolution，
对。
好，它除了原本是设计的话，它原本也是用single resolution，所以我右边的话就是修复说它是single resolution中的第resolution。
So, in this result, does it has applied mechanism? Okay, so this result is the jointly combined method. Okay, I see. Thank you. And the next one. Next one. Okay. Today we have only 3 speakers.
Hello everyone. My name is and my advisor is Today I'll present my work, Underwater Formation Model Guided Spectral Channel Attention Network for Underwater Energy Enhancement. Here's the outline of my presentation. I will first introduce the background and challenges of underwater energy enhancement. Then, I will explain our proposed method and show experimental results. Finally, I will conclude the presentation. Underwater images are important for many marine applications, such as ocean exploration, underwater rovers, and object detection. However, underwater images often suffer from poor visibility. This is mainly caused by light absorption and scattering in water. As light travels underwater, different wavelengths are absorbed at different rates. Red light disappears first, while blue and green light can travel farther. At the same time, particles in water scatter light, producing haze, blur, and low contrast. Therefore, underwater images usually appear dark, blurry, and strongly blue-green. Improving their quality is essential for both visual observation and computer vision tasks. To understand this problem, we can look at the underwater image formation model. The captured image is composed of two parts. The first part is the clean scene information weakened by transmission map. The second part is the background light caused by scattered ambient illumination. In theory, if we can estimate the transmission map and background light correctly, we can recover a clearer image. However, this is difficult because depth, water condition, and scattering properties are unknown for a single image. This motivates us to use physical information as guidance in our network. These figures show how light absorption changes with depth. As depth increases, red light is absorbed first, and the image gradually becomes dominated by blue or green colors. The overall brightness also decreases. The examples on the right show the same change. Images captured at greater depth become darker, less colorful, and harder to recognize. There are three major challenges in underwater imaging. First, wavelength-dependent absorption causes severe color distortion. Second, scattering from suspended particles reduces contrast and creates haze. Third, refraction and water movement may introduce distortion and blur. These factors make underwater image enhancement a challenging task. Existing methods still have some limitations. Spatial domain methods, such as CNN or game-based approaches, can enhance local details, but they may also amplify noise. Frequency domain methods can capture global information, but many of them focus on spatial frequency and do not fully explore channel-wide spectral relationship. Physics-guided methods use useful physical priors, but directly injecting estimated physical maps may cause error propagation. Recent MAPA-based methods have strong sequence modeling ability, but they usually lack explicit physics-guided frequency modulation. Therefore, our goal is to combine physics priors, frequency domain modeling, and channel-wise attention in a unified framework. Here's my proposed method. The proposed UFN SCA net follows a U-shape encoder-decoder architecture. The encoder extracts small-scale features through receiver blocks and downsampling. The decoder reconstructs the enhanced image signals. This helps reduce the risk of error propagation. The second part of PSCA is spectral channel attention. First, we applied global average flow to a feature map to obtain a channel descriptor. Then, we apply Fourier transform along the channel dimension and separate the spectral representation into amplitude and phase. The amplitude contains intensity and contrast information, while the phase is related to structural information. Next, we combine these structural features with the physics prior and feed them into a Mamba block. The Mamba block models long-range channel dependencies and generates adaptive modulation weights. These weights are used to adjust amplitude and phase. After inverse Fourier transform, the enhanced feature is added back to the original feature map through a residual connection. In this way, PSCA can enhance degradation-related spectral channels while preserving important image structures. Our chaining objective contains two losses. The first is the reconstruction loss, which combines L1 loss and SSI loss. It helps the output image stay close to a ground truth in both pixel values and structure. The second is the underwater formation loss. Using the estimated transmission map and background, we reconstruct a physically possible clean image and compare it with the ground truth. This loss encourages the physical estimates to be more consistent with underwater imaging model. The final loss is a weighted combination of these terms. And here is my experimental result. We evaluate our method on 3 paired datasets, P90, LSBY, and UFO 100. Instead of going through every number, I would like to highlight the main trend. Our method achieves the best or very competitive performance across all 3 datasets. Compared with existing methods, it shows strong PSNR and SSI performance, especially on more complex degradation cases. This indicates that our method can effectively improve image quality while preserving structural details. We also test our method on 2 unpaired real-world datasets, UCCS and U45. Since there are no ground truth images, we use no reference metrics, such as UIQM and UCIQE. The results show that our method achieves strong perceptual quality and color neutralness. This suggests that our model generalizes well to real-world underwater scenes, not only to paired benchmarked datasets. Now, let us look at the visual comparisons. Some baseline methods yield the obvious color cast. Some methods over-enhance the image and produce unnatural colors or artifacts. Others improve brightness, but fail to recover light details. In contrast, our method produces more natural colors, clearer structures, and better contrast. The results are visually closer to a ground truth. These visual comparisons are consistent with the quantitative results. To verify the contribution of each component, we conduct an ablation study. When we remove the Mamba block, the performance decreases, showing that adaptive channel modeling is important. we remove spectral channel-wise attention, the performance also drops. This confirms that channel-wise frequency modeling is useful for underwater enhancement. Removing the physics prior or the underwater formation loss also reduces performance. This shows that physical guidance helps improve both enhanceability and robustness. Overall, each component contributes to the final performance, and PSCA is the core model of our framework. To conclude, we propose UFM SCAN, a physics-guided frequency domain framework for underwater energy enhancement. The main contribution is the PSCA module, which combines channel-wise further attention with physical priors from the underwater energy formation model. By using transmission and background information as guidance, our model can perform more adaptive and physically meaningful spectral modulation. We also introduced an underwater formation loss to improve physical consistency during changing. Experimental results on multiple datasets show that our method achieves strong quantitative and visual performance. For future work, we plan to extend this method to video-based underwater enhancement and explore real-time deployment on edge devices. And here's my reference. Thank you for listening.
Thank you. Okay.
What is the difference between your method and previous frequency domain method?
Many previous frequency domain methods focus on spatial frequency information. Our method instead explores the channel-wise frequency representation. This is important because underwater degradation is strongly related to channel-wise color attenuation and imbalance. By modeling spectral relationships along the channel dimension, our method can better handle color distortion and contrast degradation.
Okay. How do you prevent over-enhancement on underwater images, like overly sharpened texture or amplified noise in your model design or training process?
Our method avoids over-enhancement in two ways. First, the physics prior provides guidance so the network does not blindly enhance all regions. Second, PSCA performs adaptive spectral modulation through residual learning, which means the enhanced features are added back to the original features instead of completely replacing them. This helps preserve natural appearance and reduce artifacts.
Okay, further question? I have. Your method is designed and dedicated for the underwater environment, right?
Yes.
And can it also well performed in the normal environment such as Earthground or deeper sea? You have a page show the wavelengths and so as I think maybe the environment is above a couple tier if it's deeper or in the ground earth, does your method can also well perform?
Yes, I think so, because there's also some hazy things on the upper ground. So I think we can also deal with some hazy images or even underground because it's dark and the underwater images are also dark. So yes, I think so.
Okay. So this method can well adapt to different environments.
Yes, including hazy or like with some particles or dark things.
Okay. Thank you.
Thank you.
We welcome the next one.
Morning, everyone. My name is Chen Guanhao, and my advisor is Professor Wang Jiabing. Today I will present our work title, Adaptive Multi-Objective Mobile Optimization for Low Earth Orbit Satellite Networks. This will focus on mobile optimization in low Earth orbit satellite network using a drawing equivalent-based reinforcement learning framework. First, I will briefly introduce the background of sixth generation and LEO satellite communication. Then, I will review existing handover method and explain their limitation. After that, I will introduce our proposed deploying framework, including the system model and remote design. Finally, I will present the simulation result and conclusions. From first generation to sixth generation, wireless communication system has evolved significantly in terms of data rate, latency, and service capability. In sixth generation network, the target data rate can reach up to 1 terabit per second with ultra-low latency and global coverage. Compared with traditional terrestrial communication systems, sixth generation also integrates non-terrestrial networks or NTN such as satellite communication systems. This makes LEO satellite networks an important technology for future global connectivity, especially in remote or underserved regions. First, let's understand the background knowledge of satellite communication. In satellite communication, satellites are classified into low Earth, medium Earth, and geocentrics based on their orbital altitude. Because low Earth orbit satellites are closer to Earth, LEO has lower path loss and propagation delay than GEO. Thus, low Earth orbit satellites are suitable for communications. However, low Earth orbit satellites have a small coverage area and move fast, moving 7 kilometers per second, leading to frequent handover. We need an effective strategy to reduce the number of handovers. Next, let's discuss the background knowledge of satellite handover. Handover in terrestrial base station communication is based on signal strength. When the user moves, the distance between the user and the base station can change, and the signal strength change accordingly. Therefore, the base station can determine when to hand over to which target station based on the signal strength. However, in satellite communication because the distance between the user and the satellite is very far. The user movement will not change too much to the distance between the satellite and the user. So the signal strength will not show obvious changes. This also makes it not suitable for use traditional handover method to determine the timing and target of handover. Therefore, we need to design the new satellite handover method. This method will not take into account the characteristic of the satellite objects. In our scenario, we consider several user equipment located in a remote town. Since this area is far from the other cities, the satellite system mainly focuses on serving users within this local region. Due to overlapping satellite coverage, each user may observe multiple visible satellites at the same time. The system therefore needs to dynamically determine which satellite should serve each user. Existing satellite handover methods often utilize predictable satellite trajectory. Because satellites move on fixed orbit, user can estimate how long each satellite will remain visible. Based on these characteristics, several handover algorithms have been proposed using visible time or resource availability. However, this method usually optimizes only a single objective. For example, NBT select the satellite with the maximum visible time. MAC select the satellite with the maximum available channels. GPW using graph-based optimization. MSH and MSHBO focus on reducing handover cost and blocking probability. Although this method includes specific metrics, they still have several limitations. Some methods cannot balance blocking probability and handover cost simultaneously. Some optimization-based methods are computationally expensive and difficult to deploy in real-time environment. And conventional DQM-based methods may suffer from unstable decision-making. Our motivation comes three major challenges in aerial satellite networking. First, frequent handover may cause serving interrupt and throughput degradation. Second, existing methods cannot effectively balance throughput, blocking probability, and switching costs at the same time. Third, optimization-based approaches are difficult to apply in dynamic real-time scenarios. To address this issue, we propose an adaptive multi-objective handover optimization framework based on built-in DQM. The proposed framework can dynamically balance different objectives according to changing network conditions. The main contribution of this work are as follows. First, we formulate the handover problem as an adaptive multi-objective optimization problem. Second, we develop a dual-in DQM-based framework for dynamic satellite selection. Third, the proposed framework improves handover stability while reducing unnecessary switching. Finally, simulation results demonstrate that our method outperforms several conventional approaches, including MBT, MAC, GPW, and conventional DQM. In our system model, we consider multiple for communication. When the serving satellite changes over time, a handover occurs. These form a dynamic and time-varying decision problem. We define a binary association variable to indicate whether a user is connected to a specific satellite. Each user can only connect to one satellite at a time. At the same time, each satellite has limited serving capability. Capacity. If the serving satellite changes between consecutive time slots, we count it as a handover event. This model allows us to analyze both resource allocation and switching behavior in the network. The achievable transmission rate is calculated based on the Shannon capacity formula. System throughput is defined as the total achievable data rate of all users. Blocking occurs when the satellite cannot accept additional user because of the limited capacity. Therefore, our system jointly considers throughput, blocking probability, and handover cost. We model the handover process as a marker decision process. The state include candidate, satellite load, throughput, and the previous serving satellite. The action is select the serving satellite from the visible candidate sets. The reward function jointly considers throughput, reward, blocking penalty, and handover penalty. Instead of using fixed rate vector, our framework dynamically adjusts the objective rate according to network condition. This slide shows the overall architecture of proposed framework. The tooling DDQM contains two streams, the value stream and the advantage stream. The value system stream evaluate how good is the current state is, while the advantage system evaluate which action is better under the current state. Compared with conventional DDQM reviews Q-value over estimations. Meanwhile, the tooling architecture improves decision stability, especially in overlapping satellite coverage. Environments where several satellites may have similar utility values. As a result, the proposed framework can learn more stable and effective handover strategies. This figure shows the blocking property under different user entity. As the number of users increase, blocking probability also increase because satellite resource become limited. However, the proposed during DDQM consistently achieve the lowest blocking probability among all methods. This demonstrates that our framework can effectively perform adaptive over handover optimization. This figure compares the average number of handovers. NVIDIA achieved low handover count because it prioritizes long visible time. However, some methods may introduce excessive switching under dynamic traffic conditions. The proposed method maintains relatively stable handover performance while avoiding unnecessary handovers. This shows a better balance between connection stability and resource utilization. This figure shows the system throughput performance. As user density increases, throughput decreases decrease because resources become limited. However, the proposed fluent curriculum still achieve higher throughput than conventional method in most scenarios. This improvement comes from effective satellite selection and long-term optimization capability. In conclusion, this work proposes a fluent curriculum-based effective handover framework for LEO satellite networks. The proposed method jointly considers throughput, blocking property, and switching cost to effective multi-objective learning. Simulation results show that our framework achieves lower blocking probability, more stable handover performance, and higher throughput compared with conventional approaches. Overall, the result demonstrates the effectiveness of response learning for dynamic handover optimization in future LEO satellite communication systems. This is my reference. Thank you for listening.
Any question? Okay.
How does the agent dynamically balance the different objectives instead of favoring only one metric?
The agent learns the balance through long-term interaction with the environment. Under different network conditions, it automatically adjusts its decision focus to maximize calculate reward rather than optimizing only a single mesh.
Any further question?
Can you return? You have three performance metrics, including writing rate, handover cost, handover number, and also the throughput, right?
Yes.
Okay. Because normally the work in handovers will enhance the throughput, but also decrease the number of handover. So the two metrics we can compare jointly. So my question is, in the throughput, you see, you have the best performance because your throughput is better than the others. But in the handover number, you can you did not achieve the best, right?
Yes.
So I think maybe some recent inherent, some recent will cause this result. And my opinion is maybe your work is not the perfect, but it may be the second optimal. Okay. So maybe you can, if you have more time, you can think how to resolve this question. OK， 如果可以的话，因为在这边这个 handover 的数量通常会跟那个 throughput 它算是那个同步的，handover 的数量越低，throughput就越高但是你这边的话看起来就是有那么一点点可以改善but hopefully it can get a good performance. And the second question is in the reference. Okay, reference. You have compared the result with reference, right?
Yes.
Okay. Can you just briefly conclude one method which is similar like it? The most similar like it. Okay. Which one?
I think it's seven. Correct.
Which one? 7? The 7. Okay. A graph test. Graph test. Does it apply air? Air?
Yes.
Okay. This one is the most similar method like you want. Okay. So, if we don't have further question, this is all today.